This is Algebra 2 with trig. We're working with section 8.2. We're going to graph our rational functions. So a rational function will look like a graph which is called a hyperbola. It has two different branches. Notice that it does not touch the y-axis and it also does not touch the x-axis. It doesn't cross it. So those lines are called asymptotes. A rational function has the form of px over q of x. And those are polynomial expressions that could fall in the numerator and the denominator. But realize that the denominator cannot equal 0. We're going to be looking at what's called an inverse function. It's a rational function also. Is 1 over x. That's particularly what this graph is. So it's considered to be the parent function. It's known as a hyperbola. And a hyperbola has two branches that are symmetrical to each other. So if we know the points on one side, we can count to identify the points on the other branch. The domain and the range. The domain are the x values you can plug into your equation. So you can plug any number into your equation except where you get the denominator to be 0. So that's why they call it non-zero real numbers. You cannot be 0 in this case because that would make the denominator 0, which is an undefined. And then the same thing goes with your range. This expression, 1 over x, could never equal 0. The only way to make a fraction equal 0 is to have the top of the fraction be 0. The top of the fraction is 1, so it can't equal 0. So that's why your graph never touches 0. It gets really close. 1 over 10, 1 over 100, 1 over 1,000. It gets really close, but it's never quite 0. And then we have our form of a over x. A could be any number. In this case, a is 1. That's the parent function. But it could be a 2 or a 3 or an 8, a -3, a -4, any number. So we're going to try this down here. We're going to take a look at 4 over x. We're going to try to graph that. This is, the parent function is 1 over x. So this is 4 times. This is stretched vertically by a factor of 4. So you could put in your parent function and then stretch it by a factor of 4. That's how we do it in the past. But there are other ways that we can do that. The first thing we'd want to do is identify our vertical asymptote. The vertical asymptote is whatever x value, or any x value, maybe that's better, any x value, whatever x value makes the denominator 0. So, whatever makes the denominator 0 is going to be your vertical asymptote. So in this case, it's pretty clear. It's just 0. So your vertical asymptote is going to be 0. It's where x equals 0. And your horizontal asymptote is wherever your fraction can equal 0. Your fraction here cannot equal 0. Well, the horizontal asymptote is the number it can't equal, and that is y equals 0. Because a fraction can never equal 0. This fraction can't. Now we can draw in our asymptotes, and we label it on the graph as x equals 0. And we'd also draw in our horizontal asymptote. We could say y equals 0. So we're never going to get 0 as an answer, and we can't use 0 as a number to plug in. So we're going to pick 3 numbers to the right side of the vertical asymptote. Pick any 3 numbers you want. I would suggest, if you're going to try to be smart about what numbers to use, pick numbers that go into 4. You know that 1 goes into 4, 2 goes into 4, and 4 goes into 4. So we could try that. When x equals 1, we get 4 over 1, which is clearly 4. So we can plot that point. And when x equals 2, we get 4 over 2, which is 2. So when we're out here at 2, we're up at 2. And then we'll take our last value, and that's where x equals 4, and we plug that into our equation. That gives us a value of 1. So over 4, up 1, and that can give us our first branch. Makes it real clear where we would draw in and connect our dots. So now we have to figure out where to draw it on the other side, the other branch. You could come over here and pick any points that you want. Or you can use the idea that this is symmetrical. That's what I'd like you to do. We're going to go 1 to the right and up 4. Well, symmetrical would be 1 to the left and down 4. 1 to the left and down 4. If you plugged a -1 in here, you'd get 4 divided by -1, which is -4. To the right 2 and up 2, to the left 2 and down 2. So at -2, we get -2. If you tried it, you plugged in -2, 4 divided by -2 is -2. 3 doesn't go into 4 very well, so that's why we moved over to 4. 1, 2, 3, 4 to the right and 1 up. 1, 2, 3, 4 to the left and 1 down. So we're just making it symmetrical on both sides. So that's our equation. We like to write y equals 4 over x. Your domain is always any x value that you could type in to get an answer. 4 to the left and 1 down was -1. So your domain are your x values that give you answers. So you can plug in any x value, all real numbers. You can get any value. The graph covers all the x's except where x is the asymptote, where x equals 0 in this case. And your range, what y values can we hit? We can hit all the values down, we can hit all the values up. What we can't hit is we're all real numbers except where the asymptote is at. What we can't hit is y equals 0. So in our comparison, we don't see a negative in front of the 4, so there is no reflection. In our comparisons, we like to do R, S, and T. There is no reflection, but there is a stretch. Stretched vertically by a scale factor of 4. Because this value is 4 times the 1. 1 times 4 makes that. There is no translation. We haven't moved the asymptotes off the axes. Alright, these are the rules for translations. So when we're working with translations, we're dealing with H's and K's. So similar to other types of equations we've had and dealt with H's and K's, the H moves it right and left, the K moves it up and down. So the asymptotes we're going to draw are going to be located where H is. X equals H. That is your vertical asymptote, is wherever the H value is. Remember, it's going to be the opposite of what's inside here. So if it's x minus 2, then it's x equals 2 is your vertical asymptote. If it's x plus 3, then your vertical asymptote is at x minus 3. X equals a negative 3. Let me fix that. And in this case, y equals k. That is your horizontal asymptote. Because what the number you can't get to is this k. Because the only way to get to k is to have a fraction that equals 0. But the fraction can never equal 0. So never equaling 0 plus the k will get you to never equal the k value. We're going to plot 3 points to the right and 3 points to the left of the vertical asymptote. We're going to draw 2 branches to make the hyperbola, and we're going to plot those points, and we're going to approach the asymptotes. Alright, this can be a little intimidating, but you can do it. So the first thing we're doing, we're recognizing that our graph is a fraction with an x on the bottom. It has an h and a k. So since the h value is 1, we know the vertical asymptote is at 1. So we know our vertical asymptote is at 1. We can draw our line at x equals 1. We also know that the k value is 2. So we can draw our horizontal asymptote where y equals 2. You want to label that on your graph. This is all compared to the parent function that is 1 over x. Now what we're going to do is pick points that are to the right. You can really pick any points that you want. It won't make a big difference. If you want to concentrate on exactly which ones you can, you could. Okay, we can pick the number 2, 4, and 7. Those would all be good locations. What happens when we try 2? When x equals 2, 2 minus 1 is 1. So we have negative 3 over 1 plus 2. So negative 3 plus 2 is still negative 1. So when we're at 2, we're down at negative 1. When x equals 4, we get negative 3. 4 minus 1 is 3, so that's a value of negative 1. Negative 1 plus 2 is 1. So when we're at 4, we're up at 1. And then when x is 7, we get negative 3. 7 minus 1 is 6. So that's a half. Now you got to be careful here. That is 1 over 2. And we're going to add a value of 2 to that. But to add 2 to that, you need a common denominator. So we call that 4 over 2. Now we have common denominators. This is a value of 2. So we're going to get 3 halves. So we got negative 1, 1, and then at 7, 1, 2, 3, 4, 5, 6, 7, just off the graph, we're up at 1 1/2. Now you could just pick any random points here to the left and do the calculations if you want. But if you like the symmetry aspect of it, going from where the axes are, we're 1 to the left and 3 down. Now we're going to go 1 to the left and 3 up. That is a total of 2 plus 3, which was 5. So when x was 0, we got the answer of 5. Now we're going to go 3 to the right and 1 down. So we're going to move 3 to the left and 1 up. So that's a total of 2 to the left and 3 up. 2 to the left and 3 up. And then we're going to end with, starting from the origin of the asymptotes, 1, 2, 3, 4, 5, 6 to the right and 1/2 down. So from that same location, 1, 2, 3, 4, 5, 6 and 1/2 up. But in reality, from the origin, 1, 2, 3, 4, 5, 2 1/2. So 2 1/2 could be considered 5 halves. So yeah, this seems a little intimidating to do those calculations. But you want to be able to not be calculator dependent. So we did that. We label our graph, negative 3, x minus 1 plus 2. Always label your graph with your asymptotes, with your equation. Plot your points. Your domain is going to be all real numbers except where the asymptote is, so x equals 1. And your range is going to be all real numbers except where the asymptote is, which is y equals 2. So when you look at your graph, you can get any y value except you'll never get 2. It'll never reach up to 2. So noticing that the 3 is negative shows that we are going to have a reflection over the x-axis. Because there's a 3 compared to the parent function, the 3 is 3 times bigger. So it's stretched vertically by a scale factor of 3. And it's translated 1 unit to the right and 2 units up. So perhaps you would pause the video now and you would try example number 3. You would first look for the asymptotes, and then you'd pick values, and then you would calculate. I would suggest, if you want some help on what numbers to choose from, I'm going to work with numbers 1, 2, and 4. So if you want your table to match mine, you could use 1, 2, and 4, and then all our calculations should come out the same. So pause your video, give this one a try, and let's see where you end up. So we're working with the graph y equals 8 over x minus 3. That comes from a parent function of 1 over x. So we look at trying to figure out what makes the denominator 0, and that's clearly going to be 0. When x is 0, the denominator is 0. So that is your vertical asymptote. We can draw in our line where x is 0. When it's right on the axes, it's kind of hard, so you might make the dashes a little thicker. So you get x equals 0. So label it on your graph. Then we also see the k value is -3. So we're going to be down here at -3. So that's y equals -3. Now we're going to calculate what happens when we have 1. So when x equals 1, we get 8 over 1 minus 3. So 8 minus 3 is 5. So when x is 1, we're up at 5. When x is 2, we could put that on our table over here. So 5. When x is 2, 8 divided by 2 is 4. 4 minus 3 is 1. So when x is 2, we're up at 1. And also when x equals 4, 8 divided by 4 is 2. Minus 3 is -1. So when x is 4, we get -1. Now remember, we can cross the axes, x-axis, as long as the asymptote is not the x-axis. The asymptote, the horizontal asymptote, is down here at -3. So when we draw our line, it's okay to go through the x-axis, but it's not okay to go through -3. Now looking at your vertical asymptote, we moved 1 to the right. 1 to the right, 3 and 5 more, so that's a total of 8. So we have to go 1 to the left, which is -1, and go down 8, which was 3 and 8, which is 11. You don't have to totally recalculate it, unless you like to. So that's going to pretty much be off our graph. Not pretty much, completely. Then, here we had gone 2 steps off the vertical asymptote. So we're going to go to the other direction. That puts us at -2. 1, 2, 3, 4. 1, 2, 3, 4. So we're down here 4 below that and 3 more, which is a total of 7. 7 below the x-axis. So that's almost on the graph again. And then our last point was from the asymptotes. That's where we want to go from. 1, 2, 3, 4 to the right. We slid to the right 4, and from the asymptote we went up 2. So we have to slide to the left 4 and down 2. So really that's 4 down 5. So that allows us to put our graph in here. and you always label your graph. Y equals 8 divided by x minus 3. Your domain is all real numbers except for the asymptote. And your range is all real numbers except for the asymptote. Your your transformation does not have a negative, so there is not a reflection. It is 8 times as big as 1, so it's 8. So that's a vertical stretch by a factor of 8. Stretched vertically by a scale factor of 8. And then the translation, there was no H value, so there was no right and left translation, right or left. There is a down, so it went down 3. The K value is negative 3. So we translated down 3. You can tell that by looking at the asymptote. The asymptote typically would be at the x-axis. It's down 3. So now you know that there was a translation of 3. Last question. We look at the time in lowercase t for seconds that it takes sound to travel 1 kilometer. It's this formula. So now what we're going to do is t equals 1,000.6 times 35, because we're 35 degrees Celsius, plus 331. When we calculate that out, we have 1,000 divided by, you've got to use parentheses for the denominator. So order of operations happens. All that goes into the denominator. It's a binomial. And we get 2.84 seconds. But that's for 1 kilometer. We now have to times that by 5. So we're going to times that by 5. And we get 14.20. 14.20 seconds to travel 5 kilometers.